New information will change your estimates of the probability of an event. Here's an example. Suppose we roll a fair die. Let A be the event that the outcome omega is even. In that case, the probability of A is 3 out of 6, i.e. a half. Next, let B be the event that the outcome is strictly greater than 3. The numbers greater than 3 are just 4, 5, and 6, so again the probability of B is 3 out of 6, in other words a half. Now let the conditional probability of A given B denote the probability that the outcome is even if we know that the outcome is strictly greater than 3. In other words, this conditional probability is the probability that A occurs given that we know that B has occurred. What is this conditional probability? Well, in this case, we know that the outcome is either a 4, a 5, or a 6, and two of those numbers are even, namely 4 and 6. Hence, the probability is 2 out of 3. Hence, initially, before we know that B has occurred, we estimated that the probability of A is equal to half, but the information that the event B has occurred has updated this probability, and it is now 2/3. Let's now consider how to compute conditional probabilities on a finite sample space where each outcome is equally likely. In other words, we have a finite sample space omega consisting of n equally likely outcomes. Here the number of elements in omega, denoted with these vertical lines, is equal to capital N, and the probability of any outcome is equal to 1 over n. Now let A and B, subset of omega, be events where the number of elements in A is n sub A, and the number of elements in B is n sub B. If we repeat this experiment many times, the event A will occur a proportion of NA over n of the time. In other words, the probability of A is NA over n. Similarly, the probability of B is NB over n. We now ask, what proportion of the time that B occurs does A also occur? Well, if A occurs when B also occurs, then the event A intersection B must occur, because both A and B occur. This will happen a proportion n sub A intersection B divided by n sub B of the many times that B occurs. Thus, the probability of A given B is equal to n sub A intersection B divided by n sub B. This is the same as n sub A intersection B divided by n sub B divided by n. At the top here, we just have the probability of A intersection B, and at the bottom, we have the probability of B. And thus we define the probability of A given B as the probability of A intersection B divided by the probability of B. Now notice that if we multiply through by the probability of B, then we obtain that the probability of A given B times the probability of B is equal to the probability of the intersection of A and B. And by symmetry, that will be the same as the probability of B given A times the probability of A. We will now consider two important rules for computing probabilities. First, we have the law of total probability. The probability of an event A is the probability of A given B times the probability of B, plus the probability of A given B complement times the probability of B complement. Note here that B and B complement are mutually exclusive, in other words they are disjoint, and also that the union of B and B complement is the entire sample space omega, in other words that they are exhaustive. More generally, if B1 up to Bn are mutually exclusive and exhaustive events, and by that I mean that any two have empty intersection and that the union of all the B's is the entire sample space, then the probability of A is simply the probability of A given B1 times the probability of B1 plus the probability of A given B2 times the probability of B2 all the way up to the probability of A given Bn times the probability of Bn. We'll give the proof here for the case where n is equal to 2. Since A can be written as follows, A is equal to A intersection B union A intersection B complement, and since these two sets here are disjoint, we see that the probability of A is simply the sum of the probabilities of each of these sets. Now using this rule over here, we see that the probability of this intersection here can be written as follows, and similarly the probability of this intersection here can be written as follows. Next we state Bayes' theorem, a remarkably important yet simple result. The probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. To see this, start with the right hand side and write the probability of B given A as this ratio here. Cancel out the probability of A's, leaving this result here, which is equal to the probability of A given B by definition. Lastly, we consider what it means for two events to be independent. Intuitively, two events A and B are independent if the knowledge that B occurs does not change your estimate of the probability that A occurs. In other words, the conditional probability that A occurs given that B has occurred is equal to the probability that A occurs. The fact that we know that B has occurred has not led us to update the probability that A occurs. Using the definition of the conditional probability, we obtain the following. Now here we're dividing through by the probability that B occurs, and so this definition doesn't work if the probability of B is 0 because you cannot divide by 0. So if we rearrange it, we obtain the following result, and we take this to be the definition of independent events. A and B are defined to be independent if and only if the probability of the intersection of A and B is equal to the probability of A times the probability of B. In particular, it follows that if B has probability 0, then B is independent of every event A. We also note for the first time something that we will encounter again and again, namely that when we are dealing with independent events, we multiply.